I have a question
Yeah.
relating to your comment here. 1 and 2 can be the same only in classical limit h bar go to 0. What does it mean?
What does that mean? Yeah, right. So let me give you a little bit of um, background to this statement. This statement is finally coming here from the entire discussion here. So what Dirac says is that Dirac uses classical mechanics intuition here. He says that if you take in the classical mechanics, you have something called canonical transformation, and in classical mechanics, your degree of freedom x is an implicit function of time, and the problem of classical mechanics is to formulate an equation of motion for x, which can be solved to get the function of time. This is what you do, and then when you solve it, then you get the solution to the problem. But coming to the Euler-Lagrange equation or the Hamilton's equations, depending on what kind of what characteristic function you are using, Lagrangian or Hamiltonian, this is what basically you are doing. You are trying to find the equation of motion for the degrees of freedom, which is, to start with, is an implicit function of time, and the goal is to make the explicitly the time dependence of it. Now, if you start out with, so there is a trajectory, that means because x of t in the xt plane, there is a trajectory. So if this is an earlier time and this is a later time, x evolves like this. The degree of freedom evolves like this. Now, what this canonical transformation discussion does, it says that this value of the degree of freedom, x, if you look at the Hamiltonian formulation of the problem, it is happening in phase space. So it is not only x, but x comma p. So both of them are implicit functions of time. Now, so in the phase space, there is a trajectory, x and p both changes. So this is xi and pi. And then there is an xf and pf at a later time. So what you can do, it is a property of the dynamical system, that this can be viewed as a canonical transformation of the initial values. You can give a canonical transformation from going from here to here. And in the theory of canonical transformation, you see that there is it can be described in terms of generating function. And the generating function for this particular canonical transformation is action. This is a discussion that is done in additional notes, so you can look up there. If you have any question, you can ask. But this is what is happening. Now, so from this, Dirac's intuition says that this matrix element now you are doing it coming to quantum mechanics, where you cannot apply the classical mechanics discussion directly and in detail, but what he suggests that this matrix element must be related to something like this, because in the general, after developing the general theory of classical canonical transformation in classical mechanics, if you try to mimic that in quantum mechanics, then in the additional note it has been discussed that under the canonical transformation x going to x prime, you can write the matrix element between x and x prime to be given by e to the power I by h bar times g, where g is the generating function of the corresponding canonical transformation. So since this particular what we are looking at here, in classical mechanics, this time evolution can be viewed as a canonical transformation, then the corresponding generating function is action. So Dirac says that this matrix element can be written in this way. Now this has whatever has been written has a problem. The problem is what is this? We don't know what it means. Is it an equality? If it's an equality, then there is a problem in this equation, which is as follows. The right hand side is a functional of paths. So you have to give a path x of t in order to be able to calculate the action corresponding to that. Right? Is this point clear? action is dt ti to tf,
Yeah.
Lagrangian x dot and t. So you need to know these functions x and x dot as a function of time. You then plug in here in the Lagrangian and then integrate. Then only you will get the value of the action as a real number, which is the value of the action. So in the right hand side depends on the path. If you change the path, the value will change. But the left hand side does not. Left hand side has only initial point and the final point. Right. So then it cannot be equal. These two cannot be equal. Now let us. We are trying to push this suggestion, this proposal, which is not a concrete proposal, but an intuitive proposal. We are trying to find the meaning out of it. So it cannot be equal. So can it be equal for one specific path or some special path? Because in general, this changes when you change the path, and this does not change when you change the path. So if you ask this question, one answer is that what is a special path in quantum mechanics? In quantum mechanics, one special path is the classical path, where the action is extremized. So it is possible, that is a possibility. It's just an intuitively, one can say that if I have to choose a special path among all the paths, then classical path is which solves the equation of motion, which extremizes the action, could be one special path for which this is true. Now let us test that, if that is right. So first you notice that right hand side action is additive along the path. The path is between ti and tf. You can break the time interval into intermediate steps, and then for each intermediate steps like ti to t1, t1 to t2, and so on. But at for each intermediate interval, say ti to t1, this integration will give you the corresponding action, which corresponds to which is si1, which corresponds to the initial point I and final point to be 1. So, and then you have then t1 to t2 is, it is basically where is it? So the action of this entire path can be written as sum of action, value of action for the segments. So action for this part, then plus action for this part, plus action for this path, and so on. This is what one means by saying that action is additive along the path. If action is additive along the path, then this, when you write action as sum of many actions for the segments, then it will become a product. So it will be written as e to the power I by h bar si1 times e to the I by h bar s1 2, e to the I by h bar s2 3, and so on. Now, if this is a product, then for each factor has the same form like this. So each factor, according to this proposal, will be given by the corresponding matrix element. It is px. This is I1, right? So e to the power I by h bar is I1 should be equal to, or whatever this symbol is. It is between 1 and I. So it is x1 t1 xi ti. So according to the right hand side, if you take this proposal, if you follow the proposal, then the right hand side must be same as this. So I have changed the notation. I'm calling the intermediate space points to be x tilde, not x. Okay. So according to the right hand side, this quantity that we are discussing must have this form, product of such factors, matrix elements. But according to quantum mechanics, the left hand side, this similar structure can be obtained from the left hand side by inserting identity operators, many of them. and then you will get this. So now it is consistent. The right hand side it is consistent with the first observation. It doesn't solve the problem yet. The right hand side is path dependent, which is why you have only the factors where, because it is path dependent, the path knows about the intermediate points, the x tilde values, and they explicitly appear in the expression. But according to quantum mechanics, it is path independent, and therefore the intermediate values are integrated over. So it doesn't depend on the intermediate points because these are integrated over. Nonetheless, we have gotten two expressions which are similar looking. Basically, they are product of a bunch of factors, each factor being a transition element, a matrix element. In one case, the intermediate points are explicitly present. In the other case, they are integrated over. Now, why did I change the notation to x tilde? Because here they are integrated over, so the expression does not depend on them. You have integrated over them. But here they are specific values of it. So x tilde 1 is a specific value of x1. X tilde 2 is a specific value of x2. Those values are only present here explicitly. Now, we have come back to the same problem that we started out with, saying that this is path dependent, this is path independent, so they cannot be equal. And then we ask, could we find a special path for which they are equal? So we have now found a more concrete mathematical expression on both the sides. One is this one, and the other is this one. So the same question, if we ask with correspond for these right hand sides here, these two right hand sides of equation 1 and 2, you would ask, under what condition could this and this be same? And the answer is that if you take h bar going to 0 limit, then they will be same, and that will be that is a stationary phase argument that will be discussed later. But you asked what is the meaning of this statement. This is the meaning of the statement, that in the h bar going to 0 limit, although it is path independent, the right hand side is integrated over all the intermediate points. But if you pick the h bar going to 0 limit, the metric, that is the classical limit. How does a quantum mechanical matrix element, which is path independent, become only classical path? How? Because then the way it happens in the h bar going to 0 limit, you have to give a mathematical argument behind that. That argument is called stationary phase argument. Due to that argument, when you take h bar going to 0 limit, among all the other paths contribution go to 0, only one path contributes in the matrix element. And that's a classical path. So that is how, although in quantum mechanics you have, it's a path independent, you have integration over paths because you have integration over the intermediate values. But in the h bar going to 0 limit, only one set of intermediate values will be picked, because we know that h bar going to 0 limit is a classical limit. In the classical limit, a classical path will be chosen. How that happens in detail mathematically, that is the stationary phase argument that I have given later. Is the statement clear?
Yeah.
So basically, just to complete this, what I just said. So basically, we were trying to relate this. We asked, how can they be equal? And we saw that there is a path dependence on the right hand side. There is no path dependence on the left hand side. But and if you mathematically try to mathematically pose the question, then you see that this factor can be written in a factored form, provided we integrate over the intermediate points. But this expression demands that those intermediate points are fixed, because we have to choose a particular path here. So Feynman then says, well, we can improve this situation by demanding that this relation is true when Ti and Tf are infinitesimally close to each other, so that there is no path dependence. If it is a finite difference, then there are infinitely many paths that you can draw. But if if you choose 2 points infinitesimally close to each other, then path difference between 2 infinitesimally close points does not matter, because the difference will be even smaller. So variation coming from the path will not affect, and in that case we can identify this to be the result. So the Feynman proposal is take this result to be the result for infinitesimally close points, and then if you go to actual quantum mechanics where you already have this relation, and then you have chosen T1 to Tn minus 1 in such a way that they are very closely spaced, and therefore corresponding x1s, x1, x2 up to xn minus 1 are also closely spaced. Then for this, for each such factor, you could write Dirac's expression. And that's precisely what this expression is. And that is the path integral statement.